What's up, everybody? Welcome to lecture 24 over section 5.1. Lecture 24, or section 5.1 is what I meant to say. Section 5.1 starts off talking about this idea of the area between two functions. And it goes on to give a couple different weird examples, and then to talk about integrating with respect to y as opposed to with respect to x. But it starts off with this idea of integrating the area, or rather finding the area between two functions. So with that, we have this image here, this graph, that's representing the area between these two functions, f of x, g of x, as this pink box, right? And what it's trying to ask is, or get us thinking about, is how would we find that area? Well, if we were to go back and use that series development idea that we had talked about when we initially introduced the integral, then we would need to think about these different rectangles. And the height of any given rectangle, well, that's just going to be the difference between the two functions, right? So with that in mind, that means the series development leads us to this idea here. But that idea, that representation, we already know that this is exactly equal to the integral from a to b of the difference of f of x minus g of x integrated with respect to x. So this is how you find the area between two functions. You just take the difference and you integrate. The end. That's all there is to that. So having said that, let's look at a quick example. Now let's say we were asked to find the area bounded by these two functions. What that means is that we want to find the area that sits between the two functions in an enclosed way, right? So this area here. Well, we know the way we're going to set this problem up is we're going to take the difference of two functions and we're going to integrate them through some set of bounds. Setting up that problem, we know that area enclosed by these two functions will be something like this, right? Let me actually call this one t of x minus this one's going to be b of x, integrated with respect to x. All right. So looking at this, t of x is going to represent our top function, b of x is going to represent our bottom function. Well, in this case, our top function is 2x minus x squared. So we can go ahead and start filling in some of these details. Our bottom function is x squared. Again, we're integrating with respect to x. Now we need to find out what our bounds are. Well, to find our bounds, we're just going to set our two functions equal and find out what x values correspond to those locations, right? So what I mean to say is we are going to take and set x squared equal to 2x minus x squared. Start rearranging terms. That tells us that 2x squared minus 2x is equal to 0. And finally, that tells us that Let me erase this, move it up here. So finally, this tells us that two x times x minus 1 is equal to 0. So x is equal to 1 or 0, right? In other words, what we're doing is we're setting these two functions equal to each other, and we're saying, what I want is the location where they both intersect each other. That's what setting the two functions equal to each other is finding, right? Here, we know x is equal to 1, and here, we know x is equal to 0. So now we have our bounds. The area is equal to the integral from 0 to 1 of 2x minus x squared minus x squared integrating with respect to x. Rewriting all of this, this is the integral from 0 to 1 of, we can pull out the common factor of 2 to get x minus x squared. All of that integrated with respect to x. So we have 2 times x integrated is going to give us 1/2 x squared minus x squared integrated is going to give us 1/3 times x to the 3rd power. Evaluate it from 0 to 1. At 0, everything dies out, so we're left with 2 times 1/2 minus 1/3. And that's it. That's all there is to this problem. And that's how we do these things. When we say we want to find the area bounded by two functions, we mean just that. The area that is trapped between the two functions. Now, sure, you could argue, well, there's an area over here that's bounded, and there's an area over here that's bounded, but it's not, because it goes all the way off to the left over here forever, and it goes over here off to the right forever. So it's unbounded in those two regions. The only bounded region is right through here. So to say we want to find the area bounded between these two functions is to say we want this area here. And to find that area, we can start by setting up our integral, our definite integral, which we know is the integral from a to b of our top function minus our bottom function, integrated with respect to x. We knew what our top and our bottom functions were. Then we set our two functions equal to each other to find out what the bounds are. Because that function, or these two functions rather, have to intersect each other at some set of locations, and that tells us what our area of integration, our boundary of integration, our region of integration is. That's really all there is to this. So having said that, let's check out some more problems and just dig a little bit deeper into this stuff. All right, now let's say we complicated that question a little bit more. Let's say we wanted to find the area between f of x and g of x for x equal to a up to x equal to b. So we want to find the area of this region plus the area of that region plus the area of that region. Notice I didn't say bounded this time, because if I had just said bounded, we would only be talking about this area. I said the area between the two functions for x equal to a to x equal to b. So it's an area between the functions and between our x values from a to b, right? Or for x values from a to b. How are we going to find this area? Well, this is going to require a little bit more work. A little bit. But not a whole lot. What we're going to do is we're going to start by saying, you know, in this first region, in region 1, my top function is f of x, and my bottom function is g of x. And this first region is from x equal to a up to x equal to c. So for that reason, the area of our first region is going to be the integral from a to c of f of x minus g of x integrated with respect to x. But notice our top function and our bottom function flip-flop in that middle region. So for that reason, here we're going to swap f of x and g of x inside the integral, right? So instead of f minus g, we're going to have g minus f. And this is from the region x equal to c up to x equal to d. So the area of region 2 is equal to the integral from c to d of g of x minus f of x integrated with respect to x. And finally, that last region, region 3 here, is going to be from x equal to d up to x equal to b. F of x is our top function, g of x is our bottom function. So that area is going to be equal to the integral from d to b of f of x minus g of x integrated with respect to x. Oh, okay. That's a mess. That means there's a lot of integrations here. Yeah, it does. But it brings up an important point, because notice what happens here. If we kept the order to be f minus g all the way through here, we'd have to subtract this region out, right? Because this region would come out to be a negative area. Which brings us to a point. To find the area between two functions properly, what you need to do is integrate the absolute value of their difference. That is to say, the area of that entire thing, so the area of region 1 plus the area of region 2 plus the area of region 3, is equal to the definite integral from a to b of the absolute value of f of x minus g of x integrated with respect to x. Now notice, because of those absolute value signs, we could have said the other way where it's g minus f. Both cases would have been true, because you're just taking the absolute value, right? And what those absolute values are essentially doing is getting rid of all of the signs, which is really great. Because what that means is that area, just area, period, can be evaluated as the definite integral of the absolute value of the difference of functions. And that's it. That's all there is to this idea of finding area. So to summarize that point, the area from a to b between f of x and g of x is this right here. Now I want you all to take a minute to think about what that tells us about a function and the area, let me say this another way. I want you all to think about what that means for finding the area between a function and the x-axis. Because that has a very particular meaning here, right? When I say I want the area between a function and the x-axis, what we're assuming is one of them is f of x, something is going to be f of x, the function, right? But the x-axis here is going to be considered the function y equal to 0. So you would just replace one of them with 0. So it would end up being the absolute value of your function. And you're just going to integrate that from a to b. So to illustrate that a little bit better, let me erase some of this. Let's say you have a function that looks like this. And what you want to know is not the side area, but the area proper between your function and the x-axis. So you want to find the area of that purple region. Well then, in that case, you would be integrating from a to b the absolute value of f of x with respect to x. And that's because we're assuming our second function, g of x, is just equal to 0. Now, what this ultimately does for us, or what this is telling us, is that when solving these problems, we're going to have to set our functions equal to each other and solve for these things. That's a blast, right? Like that's so much fun. So what I'm saying is, to find this c value here, to find the boundaries of integration for, or the region of integration for your first region, you're going to have to say it's integrated from a to c, but what is that c value? Well, that c value is going to be where f of x is equal to g of x, right? Now to see this in practice, let's check out a quick example. All right, so let's say we want to find the area between cosine and sine for x between x equal to 0 and x equal to pi over 2. And that area, we know, would be equal to the integral from 0 to pi over 2 of the absolute value of cosine of x minus sine of x integrated with respect to x. But hey, if we look at this graph, cosine and sine swap places, right? Cosine starts off on top, sine starts off on bottom, but at a particular point, that swaps. That swaps, in particular, at x equal to pi over 4. So we can rewrite this without the absolute values as the integral from 0 to pi over 4 of cosine's our top function minus sine is our bottom function. And this is just for the first part of that region. Right? So this is for the region 0 to pi over 4. That's this left little chunk here. I know that's probably hard for y'all to see at home. It is in the notes as well. So if you're having a hard time seeing everything on the board, because I was not thinking about the size when I actually drew it out, you can check your notes as well. But that first region, like I said, has this for an area, right? Plus, that second region has pi over 4, or is from pi over 4 up to pi over 2, and has an area of the definite integral over that region of sine of x minus cosine of x. In other words, we're just saying, yes, the area is properly this, right? but this can be expanded out a little bit. And each of these individual integrals we can solve, individually. So this corresponds to that first leftmost region, and the second integral responds to the rightmost region. We can evaluate both of those integrals and then actually get the answer. And that's how we use this idea. So those absolute values are just really there to condense the material. It says a lot all at once, but this is what it's condensing, right? Instead of writing all of that, you can write this. But when you actually solve this problem, you need to solve each of these individual integrals down here. And that's all there is to it, really. Having said that, we're going to check out one last thing, and that'll be it. So stick around, folks. All right. Now, let's say instead of finding the region between your function and the x-axis, instead you wanted to find it between your function and the y-axis. You could go through the process of finding out what that rectangular area is and subtracting the area underneath the function between it and the x-axis, like so. But that's a mess. That's going to take some time, some work. There's some other stuff that's going to happen, blah, 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 blah. This route's ugly. Alternatively, what you could do, you could say, you know, yes, y is equal to x squared, but x is equal to y to the 1/2. And this area could be found by integrating with respect to y. So your bounds change from 0 to b squared, and so does your interior function. In other words, you could just find the inverse and integrate that with respect to y. That is an option. And that's what the last little bit of the notes are trying to get at, is that you can integrate with y. Not a whole lot going on there. Having said all that, that was all I had for y'all in this lecture. Just to show that you could take either route, but sometimes it's easier just to go ahead and say, I want to integrate with y instead. That's totally all right. In fact, that, again, is what the last, I'm going to say third of your notes for this particular section are about. I'll just give you an example of that. There you go. There really isn't much to that idea. You're just saying, okay, what is my function in terms of y? Integrate with respect to y. What are my bounds? I need to know those. And that's all you really do. Having said all of that, I think that is all I've got for y'all today. If y'all have any questions, by all means, please drop me an email, shoot me a line, whatever you gotta do. You got my office hours, you got my email. Yeah. Have a good one, everybody.